Hello students, in this video lecture we will learn how to draw the molecular orbital diagram for homoatomic molecules. So let's start the topic. In order to draw the molecular orbital diagram for homoatomic molecules, there are few things that is important and we need to remember those things. So what are these things? Let's start. So we know that how the molecular orbital is formed. So the molecular orbital is formed when two atomic orbitals overlap. So when two atomic orbital overlaps, then two molecular orbital is formed. Suppose if we take an example, if two 1s, okay, two 1s atomic orbital, when they overlap, okay, so two 1s orbitals, they overlap, then they form two molecular orbitals. So what are they, the two molecular orbital? The one which have lower energy and the other which have higher energy. Okay, the one which have lower, these are the atomic orbitals. So they combine together, they overlap together and they form a molecular orbitals. So that is, this one is one molecular orbital and the other molecular orbital. The one that I have drawn in the lower end, that is this is called bonding molecular orbital. Okay, the one which is lower, that has low energy and that has low energy, so more stability, and the other one which is on the higher side called anti-bonding molecular orbital. So what is the characteristic of that orbital? That have high energy, जैसा कि हम देख सकते हैं, have high energy and less stability. So bonding orbital, so we can give the two characteristics of bonding orbital: low energy and high stability, right? Low energy and high stability, and the anti-bonding has high energy and low stability. Okay, if we consider that the atomic orbitals as a wave function of psi, then the bonding molecular orbital can be expressed as, the addition of the two wave function, and the anti-bonding can be expressed as the subtraction of the two wave function. Okay, so here the word star generally we use for the anti-bonding. So how can we express the bonding molecular orbital and anti-bonding molecular orbital for different orbitals, 1s, for different atomic orbitals, 1s, 2s and 2p? That is basically beyond 2p is not in your course, so just you have to study the molecular orbital diagram up to 2p orbitals only. So for 1s it is very easily, because we know when 1s orbital, when two 1s orbital combine, then they only form the sigma bond. Okay, so for 1s, what can we write? For bonding, I can write sigma 1s, and for anti-bonding, I can denote as sigma star 1s, as I know that the energy of anti-bonding is greater than bonding. So if I just need to compare, then sigma 1s is sigma 1s and sigma star 1s. Similarly, for 2s, I can write sigma 2s is and sigma star 2s, because no pi bond comes into picture, only the sigma bond is there, only the end to end overlapping take place here, no sidewise overlapping take place in 1s and 2s. Now when 2p comes, we know that 2p there are 3p orbitals, px, py, pz. For 2p there are 3p orbitals, 2px, 2py and 2pz. So, here which one will go pi bond formation, which will go under sigma bond formation? So, generally, so by convention we assume that the 2pz orbital undergo the sigma bond formation and the 2px and 2py undergo pi bond formation. So, if it forms sigma bond formation, then it forms sigma 2pz as the bonding and sigma star 2pz as anti-bonding. Similarly, if the two undergo on the sidewise overlapping, okay, then they form pi bond and their bonding will be 2px. Generally we consider the energy of 2px and energy of 2py almost equal, and their anti-bonding will be pi star 2px and pi star 2py. So these are the bonding molecular orbitals and anti-bonding molecular orbital for the p orbital. Okay. In order to write the energy level sequence, we just determined it experimentally that the energy level for this sigma 1s and then sigma star 1s, sigma 2s, sigma star 2s and then pi sigma 2pz, sigma 2pz, pi 2px, pi 2py and then their antibondings pi star 2px, pi star 2py, sigma star 2pz. This energy level sequence has been determined experimentally that the energy level of sigma 2pz is slightly less than the energy level of pi 2px, pi 2py, pi 2px, pi 2py, but in antibonding not true. Okay, but there is an exception. This is true, the sequence is true when your number of electron is more than 14. But if the number of electron is less than 14 or less than or equal to 14, that is in case of C2, that is in case of N2, Be2, like that. So for that there would be some exception that the energy of sigma 2pz becomes slightly more than the energy of pi 2px, pi 2py. So for that we need to change their positions. Okay, this is quite true for if the number of electrons in atomic orbital is greater than 14. For less than 14, the energies of these two get interchanged. If you need the reason for this, why if the electron is less than 14, then the energy of sigma 2pz is slightly bigger than the pi 2px and pi 2py, then I must say the in if the up to nitrogen, or if the number of electrons in the molecule in the molecule is less than 14, in that case the difference between the you can say the difference between the 2s orbital and the 2p orbital is not much more, because the difference, that is I am telling, if the number of electron is less than equal to 14, for this the energy level for the 2s and 2p is not much more. So because of that, there is a intermixing of 2s and 2p orbitals take place. They interact each other because of their very small difference in the energy, and because of that this exception comes into picture. And the three important condition for the atom molecular orbital to be formed, जैसा हमने देखा, the two atomic orbital when they combine together they form the molecular orbital, but the some condition that you just have to follow to make the molecular orbital. The first condition is the combining atomic orbital should have same energy. Since here the 1s and 1s, they are combining each other and form the molecular orbital, so 1s and 1s should have the same energy. Okay, so the two atomic orbitals that are combining together must have same energy. तो क्या condition हुई? The two atomic orbital have same energy, must have same, or you can say nearly same energy. The second condition for the formation of atomic orbital, that their extent of overlapping should be large. Okay, their extent of overlapping should be large. And the third, they should have same symmetry about their molecular axis. They should have same symmetry about their molecular axis, meaning if you want to overlap 2s orbital, sigma 2s orbital and the sigma 2pz orbital, then when they combine, they overlap, they don't form the molecular orbital because they don't have same symmetry about molecular axis. So these are the three important conditions. If it asks in the exam, what are the conditions for the molecular orbital to be formed from two atomic orbitals? So the two atomic orbitals should have the same energy, their extent of overlapping should be large, and they should have same symmetry about their molecular axis. So what information does the atomic molecular orbital gives when it is formed? So it gives the information about the stability of the molecule. It gives the information about the stability of the molecule. I'll tell you through question how it gives the stability of the molecule. The second important things, it helps to predict the bond order. It helps us to predict the bond order. It helps to compare the bond dissociation enthalpy. It helps to predict the bond dissociation enthalpy, the bond length of different molecules, and also it gives about idea about the magnetic behavior of molecular orbital. Magnetic behavior. Because of these things, we are just drawing the molecular orbital diagram in order to predict about these things for a molecule. So let's start these things, calculate these things through a question. So we need to draw here the molecular orbital diagram for N2. I'll give you very easy method, easy way to draw this the energy orbital. If you don't remember any laws, any rule for that, even then also you can draw the molecular orbital diagram for N2. For that, I must say that you must memorize the rule for N2 or the less the molecular orbital having the a number of electron less than or equal to 14, 2-1-2-1 rule जो है आपको याद रखना है. So what is this 2-1-2-1 rule? I'll let you know in due course of time. So just we need to draw the molecular orbital diagram for N2. So here if we know the nitrogen, the atomic number 7, the configuration will be 1s2, 2s2, 2p3, right? And for N2 it is 14 or less than 14. We just memorize the rule 2-1-2-1. So 2-1-2-1 rule है. So atomic number is 17, means 1s orbital, 2s orbital and 2p orbital, they overlap. Because we have another molecule N, so the one N come overlap with the other N. So we have to draw the molecular orbital diagram. Generally we draw the molecular orbital diagram for valence electron only. So in exam for the filled electron you can use KK for that, or KK star. That one is signify bonding and other is signify for anti-bonding. But right now I just tell you how to draw the energy diagram for 1s also. So कैसे draw करना है? You have two 1s, okay, because I have shown the configuration for one nitrogen, but you have two nitrogen, so you have two 1s, two 2s, two 2p. So क्या करना है? First for 1s के लिए just this I have to draw the two box, okay. Draw the two box. One is, this is 1s and this is 1s, okay. Now just इसको ऐसे करेंगे. The lower one is the bonding of, when they overlap it forms bonding and this form anti-bonding. इसको ऐसे ऐसे हमें डैश निकाल देना है चारों डायग्राम्स के लिए. ये डैश आपके लिए बहुत इम्पॉर्टेंट है, ओके. Now what you have to do, just join them with the dotted line. Now you can fill the electron. In 1s 2 electron, so here the 2 electron, here the 2 electrons, okay, and the total 4 electron. So according to above principle, Pauli exclusion principle, Hund's rule, we are just filling the electron here also. So that is the 2 electron. The lower one is the sigma and the upper one is sigma star. So this is the diagram for 1s, okay. Now if we want to draw the diagram for 2s, also we can just draw the diagram for 2s also. This is 2s, right, okay. So this is bonding for 2s. So for 2s this is bonding, this is anti-bonding. हमें क्या करना है? We just need to draw these lines because these are very important. Now 2 electrons, okay. Now first join these things, okay. I am just drawing, these are at same level because that is the condition for formation of molecular orbitals, that energies of these two must have same or nearly same. So the 2 electron here, the 2 electrons here, 1 2 3 4 sorry. So this is your sigma 2s, this is your sigma star 2s, okay. So this is the energy level for sigma 1s and sigma 2s. 1s के लिए bonding anti bonding, 2s के लिए bonding anti bonding. So since I just have to draw it for 2p also, for that I need to erase 1s and 2s. So I am just writing what I have put in the, how many electrons I have substituted in sigma 1s and 2s and all this. So just I am writing the configuration for N2. It is sigma 1s2 in 1s, 2 electrons fill किया है, and sigma star 2s, and then I filled 2 electron is sigma star 1s2, then 2s2, and the sigma star 2s2. Okay, so I have filled this much electron. Even if you don't draw this 1s, then it is also okay, because generally for molecular orbital we need to show only the outermost electron. So if you don't draw 1s, then it will be fine. So now I am going to draw for 2p. So for 2p orbital, we know that the 2p has the 3 orbital px, py, pz. So the two atomic orbitals, they overlap. So here now I just need to memorize this rule, the 2-1-2-1 rule. So what is 2-1-2-1 rule? Says that it is 2, 1, then 2, 1. This is what called 2-1-2-1 rule. Now these dash, as we know that these dash are important. Okay. Now combine that the basic model that I am preparing. Okay. Now just fill. This is 2p, this is 2p. How many electrons are in p? 3. So 3 that we just follow according to Hund's rule. Here also. So how many total electrons when they overlap? 6 electrons. Now just try to fill the 6 electron. Here it is the bonding, so it is 2px, 2py, that is anti-bonding, 2pz. So it is pi star 2px, pi star 2py, sigma star 2pz. Okay. Now total 6 electron है हमारे atomic orbital में. So when they will fill, so 1, 2, 3, 4, 5, 6. Nothing is in the anti-bonding orbital. So now if I just want to complete this, this is for 1s, this is for 2s, and for 2p, nothing is, no electron is available in anti-bonding, only the electron present in bonding, that I can write sigma 2px equal to pi 2px, pi 2p, pi 2p, y, okay, and then sigma 2pz, 2 electrons. So that is what the configuration of N2. Or in lieu of this, you can use KK also. So if I need to find the bond order, so the bond order is what? The number of electron present in the bonding molecular orbital and the minus number of electron present in anti-bonding molecular orbital divided by 2. So how many electrons are present in bonding? So if you don't consider 1s, okay, because if you need to consider 2p and 2s, then in 2p and 2s, the outermost shell, so how many electrons are present in bonding? 2, 2 in 2s2, and here 2, 2, 4 to 6 and 2 in sigma. इसमें हमारा 2 इलेक्ट्रॉन प्रेजेंट है and here the 2 electron, 2 electron, 2 electron. So total electron present in the bonding is 8 minus the anti-bonding, the total electron present is 2. Don't consider the 1s, just consider only 2s and 2p. Okay, because we need to focus about only the valence electron. 8 minus 2 is, so it is 3. So the bond order is 3. How does it predict the stability? For stability, for stable molecule, whether N2 is stable or not, Nb should be greater than Na. If Nb is less than Na or Nb is equal to Na, then your molecule is unstable. So that gives an idea about the stability, that N2 is stable molecule. And the second thing that it gives, since all the electrons are paired, no electron is unpaired. If no electron is unpaired, then the molecule is diamagnetic. So these two information is given by the molecular orbital configuration of N2. So for that we need to use the rule 2 1 2 1 2 1 2 1 and then fill the electron accordingly and just count them. So draw the molecular orbital diagram for O2. For O2 we know the number of electron is 16. For O2 the number of electron is 16, that we know that it is more than 14. So if it is more than 14, so remember we use the rule for this is not 2 1 2 1, it is 1 2 2 1. 1 2 2 1 is rule, remember, if the electron is more than 14. Okay. For oxygen, if I write the molecular, or atomic configuration, so atomic number is 8, so it is 1s2, 2s2, 2p4. 1s, 2s, 2p. Now I need to draw the molecular orbital diagram that I am drawing for the valence shell electrons only. So for 2s and 2p I am drawing the molecular orbital diagram. For 2s it is very simple. For 2s, okay, for 2s this is two atomic orbitals, they overlap, and the lower one is the bonding, the upper one is anti-bonding. This is sigma 1s, sorry, sigma 2s, this will be sigma star 2s, right. So how many electrons? 2 electrons. The other oxygen atom also have 2 electrons. That is for one oxygen atom. This is for other oxygen atom. 2 oxygen atom, they overlap and form bonding and anti-bonding. So total 4. Okay. So 2 in the bonding and 2 in the anti-bonding. Okay. Now just combine them as we did in the previous one. In previous question. So that is for 2s, the energy diagram for 2s. Now 2p. For 2p what I need to do? Here the 3 atomic orbital for 2p, right? ऐसे बनाना है हमें. Now ये बना दिया हमने for 2p. Okay. Now यहाँ क्या आएगा for atomic? How do we go? We just follow the rule 1 2 1 2. 1 2 1 2 means 1, then 2, then 2, then 1. Okay. Because here the energy level, that is come according to the actual energy level, that the energy level of sigma 2pz is less than the pi 2px, pi 2py. Okay. So this is what? Sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, sigma star 2pz, right. Okay. Now ये डैश को अब लिंक कर दीजिए. ओके. 1 2 2 1 द रूल 1, 2, 2, 1 means the number of box that it belongs. Students को यही में problem आती है how to draw this diagram. So to understand the thing is very easy, but in the exam to draw, it is difficult to draw the diagram at the time of exam. To be cautious that first I need to write the atomic orbital and then their bonding part, anti-bonding part with the rule 1, 2, 2, 1 or 2, 1, 2, 1. Simple. So how many electrons are in P? 4. So 4 electrons, 1, 2, 3, 4. 1, 2, पहले singly fill, then pairing will take place. So 4, 4, 4, total 8 electron. Just fill 8 electron. 1, 2, 3, 4, 5, 6. Now 7, 8. 7, 8. So according to the rule, we just have to, if they have same energy, then first we have to make them singly filled, then the pairing will take place. Okay. यहाँ पे हम 2 और 0 नहीं कर सकते because they all both have the same energy level. So that is the diagram. So how many, if you need to find the bond order for that, तो just check कि कितना NB minus NA by 2. So how many number of electron, bonding में कितने electrons हैं, यहाँ पे 2 है and यहाँ 6, तो total 8 electrons in the bonding. Anti-bonding में यहाँ पे 2 electrons and here the 2 electrons. So 4 electrons by 2. So this is how much? 4 by 2, which is equal to 2. So the bond order for the oxygen is 2, and since you will clearly see that the number of unpaired electrons in the picture, in the molecular orbital diagram, you see the number of unpaired electron. So we can see that it's a paramagnetic in nature. If number of if there is unpaired electron, presence of unpaired electron indicates that it's paramagnetic behavior. Okay, it's paramagnetic behavior. I'm just telling you, if it is asked for ion, like for O2 negative. For O2 negative, that is a superoxide ion, and for O2 2 negative, it is the peroxide ion. For peroxide and the superoxide, suppose, or if it can come from O2 positive also, it can come for O2 positive also. So for that, how can you predict the bond order and how can predict the stability? It is stable because NB is greater than NA. So for O2 negative, what will you do if it is asked to draw the energy level? For that O2 negative, here the number of electrons will be not 16, it would be 17. The number of electron is 17. So 1 electron is more than in O2. So if 1 electron बढ़ेगा तो क्या होगा? Here the 1 electron will come. So the number of anti-bonding becomes 5. Okay. So 8 minus 5 by 2. So in that case your bond order will become, समझ रहे हैं, 8 minus 5 upon 2 because 17 हो गया. For O2 it is 16, but 1 electron बढ़ेगा तो 1 electron हम कहाँ, यहाँ तो कहीं नहीं डाल सकते because bonding is already filled. So 1 electron हमारा यहाँ आएगा. So anti-bonding, when we put the electron in anti-bonding, so it becomes 17. 17 means it becomes 5. Still it is stable because 8 is greater than 5. Bond order will be how much? 8 minus 5 by 2, that is bond order will be 3 by 2, or you can write it 1.5. In that case, O2 2 negative, the number of electron will be 18. So 2 more electron. So 2 more electron. So here it becomes 8 minus 6 upon 2. So 8 minus 6 upon 2 meaning the bond order will be how much? 2 by 2, that is 1. So bond order will be 1. For O2 positive, it is 15. फॉर पॉजिटिव साइन नंबर ऑफ इलेक्ट्रॉन उतने लेस होते हैं जितने पॉजिटिव साइन, एंड नेगेटिव साइन जितने आएंगे उतने नंबर ऑफ, जैसे O2 में 16 है, सो इफ O2 2 नेगेटिव इट बिकम्स 18, वी नीड टू ऐड इलेक्ट्रॉन. O2 पॉजिटिव 15 है, फॉर 15 the number of electrons bonding में कम हो जाएंगे. ओके, सो हेयर ओनली वी जस्ट फिल 1 इलेक्ट्रॉन, क्योंकि 16 होता तो ऐसा रहता. तो 15 1 इलेक्ट्रॉन, so 1 electron आएगा, then this become 8 minus 3, right? 8 minus, bond order will be 8 minus 3 upon 2, because एक इलेक्ट्रॉन कम होगा and bonding में से. So that will be 5 by 2 or it is 2.5. Okay, so if we check the stability, if I need to check the stability, bond order greater the bond order greater the stability. So if I need to write the stability order for this, so I found that O2 positive has bond order this. So if I just need to write the stability trend, so O2 positive with bond order 2.5 has greater stability than O2 with bond order 2, then O2 negative with bond order 1.5, and then O2 2 negative with bond order 1. So that is the trend for stability, and the stability is directly proportional to bond order. Bond dissociation enthalpy is also directly proportional to bond order. Greater the stability, greater the energy required to break their bond, hence greater the bond dissociation enthalpy. And if we consider the bond length, the bond length is the reciprocal of all the three things: bond order, bond order, bond dissociation enthalpy and stability. ये तीनों एक साथ है, then bond length बिल्कुल अलग. So bond length, अगर हम bond length की बात कर रहे हैं, then bond length, the trend will reverse. Lesser the bond order, greater the bond length. So सबसे ज़्यादा bond length इसका होगा, then इसका. Okay, your trend will get reversed if you need to write the bond length. So in this way we will see that if we able to find the bond order, then how can we compare the stability of different atomic orbitals, different molecular orbitals, how can we compare their bond dissociation enthalpy, how can we compare the bond length. So what the major difference between the atomic molecular orbital configuration of O2 and N2 that we found, if we just want to write the molecular orbital configuration for O2, so we can write the 16 electrons are present in O2, so we can just write Kk and then sigma, the outermost configuration, because for this I am using Kk, and for this I can use sigma 2s2 and then sigma star 2s2. For 2p I can write for this the sigma 2pz2 pi 2px equal to pi 2py 2, and then pi 2px equal to pi 2p 2py 1. So that is the molecular configuration for O2, and for N2 क्या बताया मैंने 14. So we can use Kk for this. For N2 it is 2p3. So sigmas वाले तो same रहेंगे, sigma star. So here the energy of 2pz becomes slightly greater than this. So इन दोनों का interchange. So pi 2px equal to pi 2py2 sigma 2pz2. So how many electron we needed? 14. 4, 6, 8, 10, 12, 14. So that is what the configuration for N2, and that This type of configuration you can easily write while drawing the molecular orbital diagram. So, that is very easy to fill the electron. If you construct the molecular orbital diagram, then it is very easy to construct. So, in this lecture we have seen the molecular orbital diagram for homoatomic molecule. In next lecture we will go for heteroatomic molecules.